Thanks for the introduction. So you've heard from Marco about probably the fastest flows in the office, so now you're getting the slowest flows in the office. So I work in partnership with Glasgow Airport, and we are looking for ways to further our understanding of wake vortexes through different simulation strategies. And the work I'll be presenting today is one of them. So it's the actuator line method for the simulation of continuously varying high lift aircraft geometries on the wake. So just the structure of the presentation. So I'll give you the classic contextual information. Then I will move on to the methodology in a high-level description. But the key thing I want to show today is the sort of in-depth application of the methodology to a specific test case. So wake vortexes. So why do we care about wake vortexes in general? Well, they're the main factor in the categorization of relative risk to aircraft on final approach and takeoff. And if I just direct your attention to the bottom left graph on the screen, so an aircraft encountering a wake vortex system can experience multiple different effects. So we have the imposed roll moments, loss of altitude, structural factors, and you can also have imposed yaw moments, just depending on the specific area of the vortex that you're crossing and the orientation of your aircraft. And these are not independent. These can happen coupled or decoupled, just depending on specific interactions. These often occur, obviously, in regions where the traffic is condensed, so on final approach or takeoff, and it's incredibly dangerous at this point because pilots have very little reaction time and even often control authority to sufficiently outmaneuver the effects of the wake vortex interaction. And that's why we have the mandatory aircraft separation distances that have continued to be used today from the research that was done about 40 years ago. I'd just like to state on the right-hand side of the screen, wake vortex damage isn't limited to just aircraft encounters, but it may also cause damage to structures, such as those observed in the top right, particularly to roofs and structures in the vicinity of the airport. So the overall goal then is how do we simulate landing and takeoff cycles in a cost-effective manner whilst retaining the key flow physics of wake vortexes. So before we get to the new methodology, there's two ways that we can analyze wake vortexes. So there's the experimental side, and that's things like LiDAR technology for in-field measurements around airports, or PIV and pressure taps for measurements inside wind tunnel experiments. Now, both of these methods are subject to issues such as environmental noise. As you can imagine, the area around active runways is quite a noisy environment. And also, these are 2D planar measurements of velocity. So if the wake vortex is subject to crosswind conditions, it can translate out with the area of measurement, and you can lead to sort of noisy observations like the orange line graph at the top right. If we want to simulate wake vortexes, well, there's a couple of ways we can do that. So we can do a full-scale simulation that includes the aircraft geometry, and also a far enough downstream wake region to resolve the flow features of interest, such as the long wave instabilities. But these are incredibly expensive because we have the refined near geometry region, including the boundary layer and the walls. But the wake also has to be sufficiently refined such that we can capture the effects of the wake vortexes with minimal dissipation from the mesh. Typically, when we simulate wake vortexes at the minute, we use mathematical descriptions. So we decouple them through mathematical formula, but these have their own assumptions and can lead to infeasible simulations. So our new methodology, so I've got the steps here, but this can work for any aircraft geometry of interest. Specifically in this case, we're talking about continuously variable geometries that deploy in time, such as high lift devices, landing gear control surfaces, but it can also be applied to stationary surfaces the same. So what we first do is we discretize the geometry. For deployable surfaces, we essentially assign discrete deployment levels and then generate meshes for simulation in the near field region with the geometry present. With the results of the near field simulations, we extract the span-wise loading through integration of the pressure, and we use that to collate into a solution database for a reduced order model. Using the reduced order model, we can predict the values of intermediate deployment on the span-wise loading. And what we can then do is we can take the two-dimensional lifting line interpretation and sweep it through the domain of interest that we are studying, for example, the runway area. And we can then propagate that in time to observe the rolling up of the vortexes and their dynamics in a physical manner without the need for the geometry in the final simulation, which lets us take the nodes that would be used in simulating the near geometry region and apply them to the far field instead. So the way we do that in SU2 is we simply apply a spatially and time varying source term in the governing equations, similar to the methods that have been done already for the body forces, except they're varying, and we evaluate the reduced order model to get the values for the force. This is obviously a pre-processing step, so this can all be done offline before simulation. A little bit more in terms of the implementation. So we made a new Vortex force class in the flow sources file, and that when you initialize that class, it'll create a connectivity table between the force tables that you supply in CSV format and the local ID that SU2 uses when solving the equations. And you can see just at the bottom a little flowchart, but essentially we advance in time, we read a new force table, we use the connectivity table to relate back to the node that dictates where the force is being applied, etc. Okay, so the test case I'll be presenting is the EET AR-12 aircraft geometry. So this is a representative medium haul aircraft, courtesy of NASA. And the reason we picked this geometry is that we have easily obtainable flat deployment settings, and we can displace them using the OpenVSP software. So what we did first of all is we scaled the geometry from the wind tunnel model to the final size. And then we simplified by removing the double slotted vanes or double slotted flaps on the left-hand image and replaced them with a continuous vane, just to make the meshing process a little bit easier. We did unstructured grid generation using GMesh, and we inserted the boundary layer post and vista generation with an advancing frontal method. Okay, so what we're trying to do is we're simulating using the meshes at the top right to then feed them into the reduced order model to get the effect of the bottom right image. And you can see just the discrete deployment settings on the left-hand table there. So after simulating the four geometries, these geometries, we can take the pressure solution, we can integrate it over the span of the wing, and that gives us the span-wise loading values. So you can see here the results of the four simulations, and that makes up the training set for the reduced order model. I should point out that we use the lift and drag integration width, and that way we can account for any discrepancies between the final size of the node, the mesh that we apply the force on, and the number of integration slices that we used. So we do the lift per unit width rather than the total lift. And that keeps it consistent for different mesh geometries in the far field. So as I mentioned, we form the training set of the reduced order model. Before we can use it in the final simulation and sweeping it through the domain, we just have to quickly validate it. And we do that via the leave one out approach, i.e. we exclude one of the inner training points and we reconstruct it using a depleted reduced order model, and that way we can get a sense of the error, some sense of the error. I should point out though that we are using a depleted reduced order model. The actual reduced order model that we use in practice may be slightly more accurate. So when we do this, we get relatively good approximations in the outboard flap region for both the lift and the drag. This discrepancy comes from around the inboard flap region, which is here and here, and we attribute that simply to the exclusion of 1/4 of the training set. So there's quite a big gap between flap setting 1 and 3, for example, if we remove number 2. So the final simulation then, so we take this reduced order model, we take our lifting line, and we're going to sweep it through a domain that spans 210 meters that is representative of the sort of region running up to an aircraft runway. We have the flap deploying from setting 2 to setting 3, and as we have removed the geometry from the simulation, we can use a structure grid. And I should also say that we base the mesh cell sizing on the assumed vortex core radius. And if we run this using hybrid RANS LAS, we get the following animation. So going from left to right is the lifting line and downstream of the lift. lifting line is the, or upstream I should say, is the generated wake as a result of the line moving through the domain. So you can see here very clearly the two distinct regions. So this one here corresponding to the inner flat vortexes, the outer flat vortexes, this region here, and then we have the tip vortexes here. And we can see that in time, from the mutually induced velocities, they are observed to move downwards. And that is consistent with what we'd expect. And that's why it's a danger to structures as well as aircraft. Just a slightly different view of the same simulation, just so you can see the downstream, the descent of the vortex pairs. You can see here, they're moving down the way and they're slowly orbiting the tip vortex, and in time we'd expect them to eventually merge into two distinct counter-rotating vortexes. The advantage of this approach, as you can see in the next video, is that we're not limited anymore to velocity variables. We can also obtain state variables like pressure, which is very important in the evaluation of structural impacts. So, for example, here we have an under pressure, I should say, of 200 pascals, that we can then use to dictate whether or not this wake vortex may pose a risk to the structures as well as aircraft. And just to validate that we've taken the geometry away, so we are going to compare the simulation with the lifting line and the extracted value of the wake downstream of the original geometry. And when we do that, we can see that the trends have been captured relatively well compared to the original CFD simulation with the geometry present for the lift and the drag. We have some discrepancies between the magnitudes here and here, but what we were most interested in is the velocity patterns, because that is what dictates the vortex roll-up behavior. So just to conclude, so our lifting line successfully captured the trends of the vortex generation with the geometry absent in the simulation. Addition of the reduced order model allows us to capture the effects of the dynamic deployment of the flap settings during the simulation. The modularity of the approach in using the lifting line allows us to sweep it through a range of trajectories that we might not have simulated previously. And we could actually further use this approach for other geometries that feature dynamic deployments, such as propellers, landing gear, control surfaces, like I mentioned. And one more thing just to point out is that, particularly with respect to propellers, we can use this with the actuator line to account for variable pitch propellers as well. I think that's it for me. So, do you have any questions?
Are you trying to consider multiple aircraft and the direction or the seat generator?
Yeah, so the reason that we've used this one is because we consider it representative of the most common type of airport traffic. So there's obviously large aircraft like the A350 that might cause more of an impact to structures, but due to the availability of the models, that's the one that we've settled for. So
okay, I also like to do more than one in the pattern for the airport.
Yeah, sure. Oh, sorry. So the question was, are we considering more than one aircraft in the final simulation? Yeah. So that's what's nice about the lifting line. We can put as many of them in as we wish, so we can have multiple or one. It's arbitrary.
Yes. Very interesting. Thank you. So not really about the work that you presented, but I was intrigued by
Yeah, sure.
you made a volume mesh increment, and then you made a polymer.
Yeah. Sure.
Do you have that polymer code available for the community if possible?
So the question was, do we have access to the boundary layer code for the wider community? And the answer is sadly not. So the code that we use is courtesy of INRIA, so it's AMG, and it's subject to their discretion, although I encourage you to contact them.
Yeah, I can add the fact that in theory the code should be available if it is just for research purposes use. So if you have an interest in using the learning, you can contact Adrian Hussein at CBR, and we'll be able to give you the code later. Any other questions?